Okay, so we first recall the Cauchy-Riemann equation we introduced last time. So definition. Cauchy-Riemann equation. Suppose your complex function u xy can be written down as fxy can be written down as u plus iv. Then the equation yields ux equals vy, uy equals negative vx. So we would like to make two remarks. Firstly, Cauchy-Riemann equation is equivalent to the single equation partial x plus I partial y f equals 0. So this is Cauchy-Riemann operator we introduced last time. Okay, and remark 2, this is remark 1. Remark 2, if partial x plus I partial y f equals 0, or f satisfies the Cauchy-Riemann equations, then we denote the complex derivative by f prime. So f prime is one half partial x minus I partial y f. Okay, and now we would like to introduce some convenient notations. So we define partial f partial z by 1/2 partial x minus I partial y f, and partial f partial z bar defined to be 1/2 partial x plus I partial y f. Okay. Then we know that if f is complex differentiable, then the complex derivative equals partial f partial z. Okay. Of course, here partial f partial z is always defined, even if f is not complex differentiable. But f prime, the complex derivative, is only defined when f satisfies the Cauchy-Riemann equation of partial f partial z bar equals 0. Okay, now we introduce the main object studied in this course. Instead of complex differentiable, this we call it holomorphic function. Suppose f is a complex valued function, complex function. So first, complex valued means u plus iv. Complex function means your variable is x and y, x plus iy. So u x y plus iv x y. On xy is where xy is a point in some open set, open domain in C, and we call f a holomorphic function, or f is holomorphic. On omega, if f prime exists and continues at each point of omega. So remark, in other words, f is holomorphic on omega is equivalent to the following conditions. Partial f partial z bar is 0. This is a Cauchy-Riemann equation. And secondly, partial f partial z is continuous on omega. Remarkable. And remark 2. About the regularity of the holomorphic function in the definition. Probably in some textbook you will see that f is only required to be complex differentiable at each point. No continuity is assumed for f prime. But eventually we will see, as soon as f is holomorphic function, it's smooth. You can take as many derivatives as you want. So for simplicity here, we will at the very beginning assume that f has at least continuous first derivative. So the point I want to emphasize is no worry about the regularity. It will not be the main topic of our course. Probably at the very beginning of the development of complex analysis, it's a basic topic, but now people find it's not that interesting. Okay, now let's look at some examples. So, example of holomorphic function. So first, we will have z to n's power function, and more generally, you have polynomial. And also rational functions. Those are holomorphic on the whole complex plane. And rational functions are holomorphic on the complex plane, excluding the points where the determinant equals 0. For example, z plus 1 over z minus 1 is holomorphic on C subject 0.1. Okay, and here we will see the advantage of the definition we given here and the criterion we given here. So we would like to make a small remark. So partial z bar equals 0. This is, later on you will be very familiar with this one because partial z bar is 1. Z and z bar are independent. But now we would like to conclude this from definition. So recall that this is equivalent to partial x plus I partial y. X plus I y. Okay, and if you compute this, what do you have? You have 1/2 1 plus I times I, which is 0. Okay, and second one is equivalent to 1/2 partial x plus I partial y, x minus iy. This is 1/2 1 plus I times negative I. This is 1. And the last one, you can either compute from definition or use a relation between the complex conjugation. So partial z bar equals complex conjugation of partial z. So it's 1. And then how to verify? Zn is holomorphic. Some convenient way is later on you will learn that. Probably will not learn in this course, but some intuitive way is partial z differential of Zn equals partial Zn partial z dz plus partial Zn partial z bar dz bar. Okay, so this is a total differential, and explicitly we verify the Cauchy-Riemann equation. From this one, you know the chain rule, so you have partial Zm partial Z times partial Z bar plus partial Z m partial Z bar times partial Z bar partial Z bar. Oh, sorry, never mind. Yeah, anyhow, if you're not familiar with this, you can just use definition partial x plus I partial y. X plus I y to nth power, and then use the chain rule. So you have 1/2 times n times x plus I y, n minus 1 times partial x plus I partial y, x plus I y. Okay, so no matter what it is, this gives you 0 because we already computed here. Later, after we learn power series, we will emphasize that to tell some function is holomorphic or not, you can expand the function into some power series. For example, f to be a summation a n m z to nth power z bar to m's power. Okay. This is any real analytic function, a power series, and f is holomorphic if and only if there is no terms involving z bar, or f is just a summation of power of zm, z to nth power. M must be 0 for the coefficient to be non-vanishing. Or a and m equals 0 for all m greater than or equal to 1. Okay, to end up with the topic we started last time, we introduced the following interpretation of holomorphic function or complex differentiable. We first look at the simplest holomorphic function, the linear function, and try to give a linear algebraic interpretation. So simplest holomorphic function fz equals a plus ib times z. If we write down f in real coordinates, we have a plus ib times x plus iv, and therefore if you write in a matrix form, then uv is A minus B, B, A times X, Y. This is a matrix product, and we denote the 2 by 2 matrix A minus B, B, A by T. And then you see a linear function. Linear function is equivalent to transformation, linear transformation also on R2 of R2. So UV just T times XY. And now, which linear function is holomorphic? Of course, not all linear functions are holomorphic. Because, for instance, X is not holomorphic. We have many ways to verify that. First, we hit it by the Cauchy-Riemann operator. And you have 1/2, or you write X by Z, Z bar divided by 2, then it's clear. The Cauchy-Riemann operator gives you 1/2. Okay, now let's turn back to the question, which linear function is holomorphic? Then actually we already compute that. That must be the transformation has this form, A minus B, B, A. And if we write down if we introduce a symplectic metric J, 0, negative 1, 1, 0, then F is holomorphic. Of course, we assume F is a linear function. Then T is commute with J. Tj equals Jt. Okay, so that comes back to my first intuitive definition of complex differentiable or holomorphic function, that linear transformation with respect to symmetry. Okay, this can be easily generalized to nonlinear functions, because we all know that calculus or derivative just a linearization of functions. Recall that we have Jacobian. F is a matrix given by Ux, Uy, Vx, Vy. Of course, here we view F as a map from R2 to R2. Okay, then F is holomorphic. I claim that if and only if J inverse Jacobian times J equals Jacobian, or Jacobian is commute with the symplectic metric matrix. You can verify it directly. This is actually equivalent to the Cauchy-Riemann equation. Proof. I omit it here, leave it to you. So this is Cauchy-Riemann equation. Okay. Now let's start another topic. So above we use the approach given by Cauchy and Riemann. Now we introduce approach given by Weierstrass, that he view holomorphic functions as a generalization of polynomials. That is another way. That is to say, he viewed the holomorphic function as power series. So first, today we will go from one side to the other one. That is, if f is a power series convergent in some radius, then f is holomorphic. And next time, after we introduce the Cauchy integral formula, we can show that if f is holomorphic according to our definition, then f must be a power series locally near each point. So locally, holomorphic functions just power series, which is an infinite version of polynomials. So from an analytical part, it's much easier than the partial differential equation. Okay, now let's talk about intuitive strategy to prove the first direction. So naively, we just use the definition partial z bar f. So what is this? This is partial summation power series equals summation of partial derivatives. So this must be summation of 0, which is 0. And also, according to definition, we need to verify partial z is continuous. So what is partial z? So we want to take derivative one by one. Or in other words, interchange the derivative and the summation operations. So you have n greater than 0, n times a and z n minus 1, and we want to show that this is continuous. Okay, now you see here we have used commutativity of summation and the derivatives several times. But this is not for free. Just in a moment, we will introduce basic theorems we learned in 521 to confirm this kind of operations. Okay, so next we will recall some basic facts from Math 521 about the power series. So from definition, the power series, just an infinite sum, have the following form: an times x to nth power. And a very important invariant or numerical quantity characterize the power series is a convergence radius. And from Math 521, we know that the convergence series is defined to be 1 over lim sup and go to infinity an. The absolute value of an to 1 over n. And lemma, I will prove it just in a moment. First, we state the lemma. So the lemma says the radius of convergence of the power series summation n equals 0 to infinity n a n z n minus 1 has the is the same as radius of convergence of the power series an times z to nth power summation. I first prove this, but before that, let's make a remark. So what is this guy? So this power series is obtained by 10 by 10 differentiation of the power series n equals 0 to infinity an times zn. So actually, that's what we had here. Okay, the proof is very easy. Recall that n times an absolute value to the 1 over n minus 1 equals absolute value an to 1 over n's power times n divided by n minus 1 times n to 1 over n minus 1. And then you take a limit lim sup. So this will be lim sup an 1 over n times 1. This is because when n goes to infinity, this index goes to 1, and the whole quantity here goes to 1 as well. Therefore, the lim sup, just a lim sup of this guy. So, but this is convergence, 1 over R, where R is the convergence radius of the original power series. Okay. Of course, then you can take derivative again, and then the good part is they share the same convergence radius. And the reason why we care about the convergence radius is because within the convergence radius, within the disk of smaller radius, the power series is uniformly convergent. Therefore, by the theorem we studied before in Math 521, we can freely interchange the order of integration, summation, or differentiation. So we collect the theorems as follows. So let fx be a uniformly convergent series of complex valued functions on the finite closed real interval AB. Then the following holds. First, if each f and x, if each term is continuous on AB, okay, then fx is continuous on AB, and okay, so this is first. And so under the same condition, Fn is continuous. So, and the integration over any closed subinterval or AB can be done term by term to give c to eta fx dx equals. Okay, so from definition, this is just from n for n from 1 to infinity, or from 0 to infinity, same thing. You can transform it by shift the index by 1. So that's from definition. And then the theorem claimed that under this condition, this equals the summation of integral of each term. Of course, here we assume c and eta are numbers between a and b. Okay, so actually this is the first statement about the continuity, and this is the second thing about the integration. In fact, an effective way to compute the integration. And thirdly, we have a statement about the derivative. So if the derivative fn prime of each fn is continuous on AB, and the power series, or the series of the derivative is uniformly convergent on AB, then f prime x, which is by definition is here. Recall that this is a real derivative, okay, because f is a function of a real variable x only. This is d dx summation an x. This can be computed by summation of derivatives of each term. Okay. So I would like to make some remark. So for first two statements, so here 1 and 2 about the continuity and the integration formula, we need to assume f is uniformly convergent. But for the second part, for 3, we don't need the assumption that fn summation fn uniformly convergence to f. Okay, we will see this from the proof, but for our purpose, we only use this formula, this kind of formula, to holomorphic functions or to power series. So usually we always have the uniform convergence. Okay, so the key point is uniform convergent. And here we assume the derivative is uniform convergent. Okay, now let's see the proof. Since you already know this from 521, I will give a very rough proof, which gives you the basic idea. So the first statement comes from the following standard 3 epsilon argument. So notice that for we have the following inequality: f c minus f eta is less than or equal to f c minus partial sum from 1 to n fk Kc and plus k from 1 to n fk Kc minus fk eta plus f eta minus k from 1 to n fk eta to derive this, you only need to apply the triangle inequalities several times on the right hand side. Okay, by the assumption, we have the following. So, by the assumption, since f and fk uniformly convergent to f, then for all epsilon greater than 0, there exists an epsilon, which is an integer, and delta epsilon k for k from 1 to n epsilon, such that the following holds. So first, we have f Kc minus summation partial sum from 1 to n Kc less than epsilon for all small n greater than n epsilon. And same thing for f eta. For n greater than n epsilon. And then if you look at the formula, the first one corresponding to the upper bound for this, second one correspond to an upper bound for the third term, and then for each of these we have the following. Eta less than epsilon divided by n epsilon this epsilon is a separate index. So for k from 1 to n epsilon and Kc and eta close enough. And combine everything, we have 3 epsilon. That is, as a consequence, we have f Kc minus f eta less than epsilon plus epsilon divided by n epsilon times n plus epsilon for Kc and eta close enough. Close enough means it's less than the following quantities. Sorry. Okay, then take n to be n epsilon. We have that f Kc minus f eta less than 3 epsilon. when C minus eta less than the minimum of delta epsilon 1 delta n epsilon. Oh, sorry, here is n. Okay, then according to the definition, since epsilon is arbitrary, then we conclude that f is continuous on AB. Then we can apply this to the second part, the integration. Just look at this one. And so this will be less than or equal to summation, the integration of the absolute value fx minus fk. So, k from 1 to n fk x dx. Okay, since f is fk absolutely convergent to f, then you will have this less than the integral of epsilon over the interval. Of course, here you need to assume the small n is greater than or equal to n epsilon. And C eta is a subinterval of AB. So as a consequence, we have limit. Okay, so I would like to write in this way. The infinite sum integration C eta fkx dx. This by definition is lim k goes to infinity summation m from 1 to k integration C eta fm x dx. Okay, and by the above argument, we know that the limit of this is C eta fx dx. So for any subdomain, subinterval in AB. Then we conclude the second one. So for the third statement, we set gx to be summation from 1 to infinity fn prime x. Then the integration from the second property, we know that this equals summation from 1 to infinity integration of each small term. And then for each one, we apply the Newton-Leibniz rule. We get this is summation from 1 to infinity fn eta minus fn C. Okay, then you have this is summation of fn eta minus summation fn C for eta C contained in AB. Okay, now let's make some remarks here. To use the statement we proved before, here we require that Fn prime x, this summation of this is converges to F prime x uniformly. Okay, and from this, for the last inequality, we only require that Fn x converges to Fx pointwisely. We don't assume it. We don't need the fact that it's uniform convergent. So that's why this assumption is a little bit different. Now we're almost there. Since G is continuous, then we can take a derivative of both sides. With respect to eta. Okay, then on the left-hand side, by the Newton-Leibniz rule of fundamental theory of calculus, we have G eta. On the right-hand side, we have the derivative of F. If we change variable eta to x, then we have a plug in the definition for f. So f n prime x equals fnx summation and prime. So that's statement 3. Okay, and now we also recall some facts. Remark. So this is done for the basic lemma basic theorem we are going to use, and then turn back to the power series. Recall that so let F is a power series. And R greater than 0 is a convergence series radius. Then F is then this one is uniformly, the series is uniformly convergent to F for x less than R, small r, strictly less than capital R. So if you draw a picture, then it says, suppose this is a convergence radius, then in any smaller disk. The convergence is uniform. Therefore, you can apply the previous theorem freely. Okay. Next, we recall a theorem about the differentiability, the continuity of partial derivatives, and the existence of total derivative. So recall proposition. So let f be a real valued function of two variables, x, y, defined on an open neighborhood U of x0, y0 in R2 if both partial derivatives, partial f, partial x, partial f, partial y, are continuous on U, then f is differentiable at x0, y0. Here, differentiable is a real differentiable with respect to two real variables, x and y. The proof is based on the mean value theorem. By mean value, notice that the mean value theorem only works for scalar valued functions. It doesn't work for the complex valued function. Therefore, here we assume f is a real function. Exists c x0, x, and y between x0 and y. So here subindex x0, x, and y means c, the choice of c depends on x0, x, and y. And eta, y, eta, x0, y0, y between y0 and y, such that the difference, so here x0, y0 is here, xy is here. So what we do is we break the difference into two parts. So this is fxy minus fx0y. Plus fx0y minus fx0y0. Okay, then you have two parts, and for each part you apply the mean value theorem. So first one you have, so first one is xy is blue one. So for the blue one you have, by mean value theorem, you view it as a function of x, y is fixed. So you have this c x0 x y y, and then for second one, the green part, you have y minus y0 partial f partial y x0 c x0 y0 y. Okay, and you write it as differentials with arrow turn, then you have the following. So this linear function is a differential, and then of course you have an arrow turn. So the arrow turn is given by x minus x0 partial f partial x c x0 x y y minus partial f partial x x0 y0 plus y minus y0 partial f partial y x0 eta x0 y0 y minus partial f partial y x0 y0. So since partial f partial x partial f partial y are continuous, on U we have this goes to the x derivative at x0 y0, this goes to the y derivative at x0 y0. And thus limit the arrow turn is all higher orders. Therefore, by the definition, the partial derivatives give the total differentiation. Okay, so a small exercise. Now you can prove Zn is holomorphic in a rigorous way according to the definition. You need to verify, you need to compute the partial derivatives, you need to verify the Cauchy-Riemann equation, and you need to verify the derivative is continuous. Okay, and a generalization can be given based on the previous theorems. So on its open disk of convergence, a power series defines a holomorphic function. So first, we noted that the derivative, this power series has convergence radius r. Then for each small r, the power series converges uniformly on z less than r. Therefore, you can take a derivative one by one. So you have the following formula. AN ZN equals this partial y ZN. And then if you compute the Cauchy-Riemann operator hitting on the power series, you get the following formula. And of course, because Zn is holomorphic, you have 0. Okay, on the other hand, we prove that the partial derivative, this one, moreover, so let's call star 1, star 2, star 1 and star 2 are continuous. So according to the definition, for a function to be holomorphic, we require the complex derivative exists, or equivalently the Cauchy-Riemann equation hold, and the complex derivative is continuous at each point. So we are done. Okay, next we introduce some very useful power series. So first, let's recall the Taylor expansion, which will be used next time as well. So let f be a real valued function of x, or a real variable x on a closed interval AB, which is continuously differentiable up to order n. Then fx has the following Taylor expansion: summation k from plus summation from 1 to n minus 1 x minus a to k's power k factorial fka plus so this is a Lagrangian remainder form for a certain Cauchy in AB. And in Math 21, we show that sine x has the following Taylor expansion. How to interpret this formula? We interpret it in this way. So the right hand side is a power series. This power series converges to sine x in uniformly in any finite region, and the cosine x can be defined similarly, and exponential x is x to n divided by n's power. And now this is a function depending on, so let's look at left hand side are functions sine, cosine, exponential depending on a real variable x. We don't know how to interpret left hand side when x is a complex number. But for the right hand side, just a power series, of course you can change x, the real variable x, to a complex variable. Therefore, this is a usual strategy we use to generalize some definition. We give some objects another interpretation, and in the new form, we can generalize it. Then the original object has a generalization. So here, we can define, so for any complex number z in C, define sine z by the power series 2n plus 1 to n plus 1 factorial cosine z defined to be z2n 2n factorial exponential z zn over n factorial. And then corollary is ez sine z cosine z are holomorphic, and partial z exponential z equals exponential z partial z sine z is cosine z partial z cosine z is negative sine z. We verify this just by the computation of the power series. And thirdly, we have exponential z equals cosine z plus I sine z. This is generalized Euler formula. Okay, and lastly, we have proposition. This rule. Although for the real part, the definition is obvious, but then for the holomorphic function exponential d, this is not so obvious, because we define exponential function by power series. Then what do you need to prove is actually z plus omega to nth power divided by n factorial equals this power series times this power series. Okay, this can be done, but probably you need the following lemma. So the lemma tells you, suppose you have complex numbers a and m, and if you first sum up all the m, and then you sum up all the n, iterative convergence series, if the total sum is less than infinity, then we can interchange the summation order in any way you want. In any order. So here S just a lattice point in the first quadrant. This is S. Okay, I will not prove this, and but for the I will not prove the lemma, and for the proposition, proof of proposition, I will just give you a hint. So you sum it up in this order. This is N, this is M. Okay, in other words, so the left hand side equals summation z plus omega L's power L factorial, L from 1 to infinity. This is L from 1 to infinity, J from 0 to L, Z to J's power, omega L minus J, L factorial times L factorial, J factorial, L minus J factorial. So this is summation L from 0 to infinity, summation J from 0 to L, Zj, J factorial, times omega L minus J, L minus J factorial. So this summation, according to the diagram on the left hand side, J equals 1. J equals 2, J equals 3, J equals 4. So you sum in this order, sorry, L equals 1, L equals 2. So by the lemma, this summation can be reordered in the following way. This can be summed as a new diagram. You first sum up M, and then you sum up N. So M from 0 to infinity, and then N from 0 to infinity. Zm M factorial times omega N M factorial. So this is Z exponential Z times the exponential omega, which is the right hand side. Okay, and then here I made a mistake, should be exponential I Z. Okay, another corollary is exponential Z plus 2 pi I is exponential Z. We can apply the previous formula and the Euler formula. Therefore, exponential Z is a period function with period 2k pi I. Okay, I will stop here. Next time we will talk about Cauchy-Gaussat theorem, Cauchy integral formula.